terminado in solution, the pH 11 to 12.5. We don't see an interesting response of the glucose detection, but in the pH process of the glucose oxidation, and we don't found anything interesting. For that, we work in 100 millivolts by second, or did this test. We try to work on concentration of 0 to 22 molar according to the ISO, and we have a good correlation about these values. We try to reply the test strip
from Pitec, Renovario, and was LP, which are Solís, Héctor Guerrero Alonso Zuna, from CECID was LP, Víctor Hugo Méndez, Miguel Ángel Vidal, Edgar Luna, and Dr. Armi Moreno. As head chief of the project, Antonio del Río de Santiago. I'm also grateful to introduce my fellow comrades that work with me at the laboratory. Here we have pictures about our team, which are hardly working to improve the systems we have at the laboratory. As an introduction, the manufacture of solar cells and its placing is highly cost. This due to the wide area that we need in order to place them, such as in greenhouses, rooftops, or lots. That's why we search for an alternative in which we can provide these areas for solar cells that are smaller. In this case, the thin films are a suitable option that we can synthesize semiconductors in glasses, such as windows, or in greenhouses, the dome, we can provide some semiconductors that will supply energy to the automation of the greenhouse. Okay, the robot task is to introduce or immerse different substrates on beakers. This will cause the growth of a semiconductor on its surface. Okay, for the automation, we need a logical circuit, a power circuit, which consists on a microcontroller, peripherals, a memory RAM and ROM. For the power circuit, we will need the logical circuit, a driver circuit, and the actuators. Now we have the dynamic model, which in this case, the SILAR technique is able to be scalable. In this case, we have this structure and a diagram that provide us with the different components from the mechanism, and through this we've analyzed through Laplace transform to make the approach of control. After this, we've already established its model, dynamic model, and we have already obtained the transfer function in order to control. Okay, As mentioned earlier, we need the logical circuit seen in section A, which consists of the microcontroller, and in the back we see the power circuit. In these first sections, A and B, we have our first approach that is still on test. Next, on section C and D, we have our latest approach, which is working finally for the automation of the technique. It includes some improves for the optimization of the process. As for the user interface, in order to the user to interact with the system, we've developed a diagram that allows us to program the system in order to interact. First, we have the crate from the author, the different compounds we can grow or synthesize, and a menu that allows us to select proof or go back in case the user already made a mistake. For feedback, we have already designed a little display that shows the number of cycles needed to complete the process, the number of cycles done, and a little legend saying the number of cycles. All this information is shown in an LSD 20x4 display. For the displacement, we have another flow diagram which compares the position of the robot in the absolute coordinates for the beakers. In this case, we compare if the robot is in the first time moving, it will immerse on the beaker, the substrate, then we continue checking for the next step, but compensating clockwise or counterclockwise the position of it in case it is needed. It also includes the different time slabs for the immersion time in regions or in races. Also for the displacement, we have the characterization of the robot. In case we need a range or establish the range for the robot, we obtain 10 RPM with a linear speed of 0.53 centimeters per second and an acceleration of 0.84 centimeters per second squared. Next, we establish the acceleration of the robot, which allows us to understand how it stops and allow us to allow us to stop it earlier or before. We obtain 200 RPM with a linear speed of 7.142 centimeters per second and an acceleration of 51.02 centimeters per second squared. We also include a sensor, which in this case was characterized through experimental tests. In these cases, this distance are the distance which the bakers are. We've encountered that the standard deviation for the distance of 33, 29, 24, and 17 centimeters are 31.96 to 33.4, 28.4 to 29.2, 23.94 to 24.04, and 60.95 to 17.25. In this case, we've done this because we need to establish how many measurements we need in order to provide of the system, which in this case was 10 measurements per 1 minute. We have now different prototypes at our laboratory, which in this case, this is the first prototype. This includes a heat iron, that's why it has this acrylic. This heat iron provides us with different approaches for the deposition of thin films. The second prototype already includes this sensor, which is in this part, and if you can see, all the system is in this little box. For the farthest and last prototype, we have this. All the system was already proven. It includes some DC motors allowing us to make magnetic steering and some different parts making it more affordable. Conclusions. The robotic system is still a functionality test. Through the all-obtained data and the dynamic model, it is programmed for carrying out several deposition processes. In the future work, a thin film of M&S will be synthesized and characterized to give the resolution of the determination. That's all from my part. I'll be glad to answer
Thank you,
questions.
Herbert. Are you the same team that Jesus? Same team?
Yeah, it's the same thing.
Well, questions? You are retired?
Thank you for your presentation. Your model depends on the room temperature.
I'm sorry, can you repeat the question?
If the experiment was room temperature.
Yeah. The thing is, on room temperature, we didn't. The methodology allows us to make the synthesize of the thin films at room temperature. That's why we didn't need a lot of vacuum or how to say this? Compressors.
Okay. Well, thank you. An applause for Herbert. Our next speaker.
La neta se me olvidó, te iba a traer la bolsa. ¿Te vas a tomar la foto, feo?
Si me dan ganas, pero es que ya se formaron. Está muy larga la fila. Yo te dije, culero. De a 200 en 200, güey. Ya. Oigan, pendejos, ya hubiéramos pedido 400 varos.
Bueno, no creo que hubiera confiado en nosotros después de habernos robado 200.
Es verdad. Pues de lo que nos dan las señoras, güey. El marketing era 200. Ay, 200. Como no soy reconocido en pinche beca de sol, pelón. A la verga. En mi casa, cabrón. Bueno, no en mi casa, bajando, güey, hay un cabrón que tiene 2 saltos deportivos. En mi cochera, ¿no? Yo con deudas en el gas. Dice que con deudas en un pendejo. Ya no. Le dije a Manuel, ya no tengo. ¿Qué? ¿Aquí lo hubieras podido tirar?
Ah, lo tiene en el baño, ya fue.
No, ¿ves? Güey, no me di cuenta de la escalera porque nunca salgo. Nunca salgo. Lo único que aprovecho de escaleras es la electricidad y ya.
¿Tú tienes de crédito?
En mi casa no lo veo.
¿Lo de evitar cargadores?
carros eléctricos?
Sí, los Tesla.
Como no atravesamos. Salta. Para contenido.
Agua caliente.
¿Qué? ¿Está buena tu té? ¿De qué es?
Ah, es de manzanilla, pero solo sabe agua caliente.
Tampoco.
Sí, solo es agua caliente.
¿Le echaste uno o dos?
¿Aquí está prepa, no?
Ah, sí.
¿No se te olvida?
Nah. La prepa en la que tuve 2 semestres nomás. Porque todo lo demás es pandemia. Que no estaba bueno.
Era agua tibia.
No.
Mira, por un lado está mal que mi prepa haya dado clases en pandemia, pero por otra parte está bien porque las disfruté.
No sé.
O sea, en enero de 2021, no sé qué ya tenía clases.
¿En serio? ¿Qué fue cuando estabas en qué año? ¿O qué?
No. Ya no hay vuelta atrás, güey. Mira,
No
primer
puede ser, ¿qué hiciste?
ya no hay vuelta atrás. Primer semestre lo llevé normal y el segundo semestre a la mitad, cuando fue en marzo lo de la pandemia. Y luego ya para diciembre ya estaba como que reanudándose y en enero se volvieron a reanudar. O sea, primero, segundo, cuarto, quinto y sexto sí los terminé normal.
No mames, yo hasta mediados del sexto entré y nos dividieron en 2 grupos. Un grupo iba a una semana, otro grupo iba a otra.
No, nosotros siguieron todos. Y digo, lo pones bueno, disfruté mi prepa.
¿Verdad que va a tomar 9?
Era morra.
¿De qué hablamos?
Parecía vato. Un cabrón así de cabello chino, ¿verdad? Sí. No, el de lo que te dije, que tenía los diagramas y todo. Era morra. Había una güey de cabello que para empezar se medía como 1.40 y el cabello le llegaba casi a los tobillos. Madre, decíamos que era el tío Cosa. Estuvo hablando como 10 minutos hasta que alguien le dijo, oiga, pegues en el micrófono porque no se escucha. No mames. Güey, está como el güey de la L. 15 números por cuenta, le dieron 15 minutos y luego de la nada le marcaron 5 minutos por el micrófono. Pero nomás te quedan 5 minutos. Se quedó, güey, adelantó como 40 diapositivas. Y yo dije, cabrón, es que se le decían eso.
Pero estaba bien nervioso, pobre cabrón.
Sí, güey.
Y luego le preguntó a la presidenta a este cabrón.
Pobrecito, güey.
Le preguntó algo bien específico.
Listo, güey.
What the fuck, ¿ya volviste a ser normal?
Vuelvo a ser normal. Ya no soy semi-gay. Ahora soy machista 100%.
Bien, evolución de personaje.
Evolución. Folksmanía. ¿Por qué? ¿Por qué te llama Folksmanía? ¿Se llama? No, güey, ¿por qué se llama gentemanía?
¿Qué vas a hacer con eso?
Lo logré.
¿No los vas a guardar como recuerdo de tu etapa?
Las guardo.
No sé.
Las guardo.
¿No has visto esos que guardan todas sus uñas y tienen un frasco lleno de uñas?
No.
Yes, como vean, pero o sea, ya.
Y una le voló al negro.
Yo no le vuelvo.
Mira, venden onigiris. No sabía que vendían onigiris.
¿Esto?
Ah,
¡Hala! Yo tampoco. Oh, pero
¿Cuánto cuesta?
bueno, está hecho en Aguascalientes, México.
ah, sí, ni cagando.
¿Cuánto cuesta?
No sé. ¿Será?
¿13 pesos?
Ah, sí.
Ah, no.
Bueno, no.
Esto más 13 y un jugo, pero no sé.
¿Quieres un sushi? No, no quiero sushi yo. No, no.
Sushi. Es un onigiri, es un onigiri.
¿Me estás grabando?
Sí.
Ah, ok. Iba a decir algo, pero mejor no.
¿Qué? A ver, museo.
Sí, claro. Te iba a decir algo de...
O nos vamos a la verdad. Ay, vamos de
esto.
No hay de otras, ¿verdad?
Ya no te va a mandar.
Esas eran las más pequeñas que había, señora.
No, estoy pensando que
Y pues pregunta si no tienen cajas de
¿Cómo?
esas.
¿Y cuántas aguas ocupa?
Pero nomás son... ¿Dónde está la pequeña? ¿Tienes sin etiqueta? ¿Al centro? No. Y déjale preguntar si tienen de esas.
de las Bonafont para que no se las quieran tomar.
Chevo.
Me voy a llevar un café porque me quedé con ganas de café. Pero un café que sepa rico.
Sería muy malo, ¿no?
Sí, demasiado.
Tengo esas mismas, pero son sueltas y cuestan 8.50 cada una. 50 el paquete.
Paco. A ver, divide 8.50, pero sí, como al revés.
20 botellas.
250.
¿Qué onda ya?
¿Vas a comprar eso?
Yo creo que sí. Me quedé con ganas de café, pero muy bueno.
¿Qué fue bueno? ¿El otro qué te pareció?
Ah, el otro sabía muy feo. Es que no tenía nada de azúcar y era puro café.
Es factible que me compre un café.
Esos están muy ricos, ¿eh?
Están muy buenos. Pero creo que no valen la pena. Están muy caros.
Sí.
No sé. No tomo café. No lo tomo. Pero me mi mami.
Me compraría un café mazapán, o café sabor mazapán.
Mi canal de café sabor mazapán.
¿Dónde?
Hay café sabor mazapán.
Sí, está muy bueno.
A ver.
Está muy endulzado. Capuchino mazapán. Está muy bueno.
¿Qué te vas a comprar?
No sé. Es lo que estoy viendo. Es mi segundo contacto con mi almohada. O sea, mi cuarto.
Ah, yo te dejo este para comprar uno de esos.
¿Tú te lo vas a comprar?
Voy a comprar uno de esos también. Para probar. ¿Qué dice tu cuenta?
Tu cuenta dice que sí. Pero no me acuerdo cuánto era el jumbo. Creo que es
¿Quieres preguntar o...?
Me parece. Muchas gracias.
29 el yugo. Creo que la diferencia entre el grande y el jumbo valga...
Sí, creo que se hace perfectamente la diferencia. Yo siempre compro jumbo porque no me acuerdo cuánto vale el grande, pero por 2 o 3 pesos creo que...
No sé cuándo elegir, ¿no? Sí, ya vi.
Sí, porque ya se me acabaron las respuestas, ya se me acabó el de aquí atrás.
Ah,
Se me
ya.
hace que ya se acabó el agua.
Y en
Pues,
este
intenta con otro, a ver si se ve.
sigue saliendo. Se acabó el agua en el otro.
Ah. No te vas a arrepentir.
O sea, ¿le echaste azúcar aparte o así nomás?
¿Cómo?
¿Le echaste azúcar aparte o así nomás?
No, así más.
Llámale son tapas. Toda la semana voy a andar así. Bueno.
Mañana sí, también se queda.
Está mejor que el anterior.
Menos el viernes. Cierra ya.
Dale, caliente. Dale. Aquí. Au, au, au. Au, au, au.
Bueno, por ejemplo, un compa tomaba creatina diaria y se enfermó y no pudo entrenar como por 2 semanas porque se chingó de COVID y su masa muscular bajó un vergo. Y no sé si el chile fue por la enfermedad o por lo del preentreno, pero él, digo, por lo de la creatina. Entonces, probablemente por eso. Pero él cree que fue la creatina y ya no la recuperación. Luego
¿Ese será eléctrico para que se estacione ahí?
no. ¿Cuánto mide? 83.
¿Cómo también con el mantel? Con este aire. Complicado. Oh, Yanan. Te cago si es eléctrico.
¿Cómo?
Te cago si es eléctrico. Lo dejo cargando. Es el gobierno ya está produciendo. ¿Pero es el gobierno?
¿Cómo?
Es el gobierno ese carro. El gobierno está produciendo carros eléctricos, no puede ser. ¿Qué opinas de este suceso?
A ver. ¿Qué opinas tú?
Que está bien. Está bien cabrón esta huevada.
¿Y el carro eléctrico?
¿Ah, sí?
Sí, se van a cargar.
¿Dónde está?
La verdad, güey.
Ahora llegando. Capaz de
Es el Congreso. Es el Congreso.
Oh, yo me meto en la tableta.
Bueno, al final compré un café de mazapán, porque me lo recomendó Eusebio. Está bueno, me gustaría un poquito más dulce, pero creo que no había azúcar ahí tampoco. A esta ciudad le hace falta azúcar. Aunque en realidad pues, está muchísimo mejor que el anterior. Lo que sí es que está calientísimo, me apenas lo puedo agarrar con la mano. Entonces tendré que esperar a que se enfríe un poquito para tomármelo. Pero sí. Ahorita no sé qué vayamos a hacer. Están ahí parados. Ah, no, ya se fueron. Ah, ya llevan. Espérense. Porque aquí va a haber más exposiciones.
So this is the investigation the study of the possible adsorption mechanism of Vacío on the surface of volcanic skyscrapers via density measuring. This is a collaborative study and it is Erica Valencia Gomez, Dr. John Miller, and Moscow, which is primarily by the volcanic eruption in the vegetal and animal respiration, the methods outside and others, which are necessary for the optimal condition of our planet, but the imbalance provoked by the anthropogenic actions have caused the temperature variability. So some of the activities involved in the production of the greenhouse gases are the industrial processes, agriculture, forestry, and water land uses, the energy and waste generation. For example, we have the Department of Quindío, a region from Colombia, in which the total of the greenhouse gases that were produced in 2016 corresponded to the 70% of the total emissions corresponded to the carbon dioxide, and it was due to some economic sectors like the agriculture and the transport. This gas, the since it not only provokes environmental problems but also health issues like dizziness and respiratory problems. Therefore, more studies of materials and technologies that can treat the CO2 are required. There are authors also proposed the graphene, a material with an hexagonal arrangement of carbon atoms like a subject of study due to its excellent mechanical, thermal, electronic, and other properties. And among its outstanding applications, there is the device for gas sensing based on transistors and flexible technology like NFC fabricated with multi-layer graphene. In the last few years, we have been investigating the functionalization of graphene with oxygen-containing groups to exploit other properties, for example, the graphene oxide nanocomposites for the removal of contaminated impurities from contaminated waters, and the carbon capture with a graphene oxide foam produced by the freezing and vacuum drying of a graphene oxide energy. So we have commented about some experimental works, and now we're going to focus on some studies that involve computational calculations. The computational chemistry and physics can allow us to obtain several properties and characteristics of a system like vibrational, optical, structural, and electronic properties of a system. This can be contrasted with experimental results to produce a complete investigation. All of this can be achieved through the density functional theory, which, as its name indicates, employs electronic density to obtain the information of interest of the operation understood. Now, we are going to check the work published by Brazilian collaborators, which investigated the absorption of a molecule of carbon dioxide and carbon monoxide in a graphene structure with a vacancy, with a single vacancy, by DFT methods in the consistent cycle, finding that the absorption occurs on the system. As we can see here in this figure, there is a fixed absorption of the CO2 places itself on the surface of the graphene at a certain distance. And when was the carbon monoxide, the carbon of this molecule enters in the arrangement of the system to form a part of the network of the carbon atoms, and it produces a chemical absorption of these molecules with a single bond. I want to show some articles that were published by several members of this investigation, like the work from Dr. collaborators, who's investigated the role of the hydroxy and epoxy bridges on the room temperature ferromagnetism of nanoparticles, finding the tarifa polycrystalline material, in which by computational calculations made in past with the gradient generalized approximation PDA function, they observe spin decompensation, the decompensation in polygon structures of graphene oxide due to the presence of the functional groups. In the case of the hydroxys, they tend to induce a magnetic moment over the graphene network, and meanwhile the epoxies tend to reduce. Another study that was published in 2022 in the American Chemical Society Mega is the analysis of the molecular and electronic properties of graphene in the low oxide coverage rate. The study was carried out as described by this flowchart, in which we started with a molecular structure that we proceeded with geometrical optimization by the using the functional linear path. Then we checked there wasn't any imaginary frequencies to continue with energetic optimization, and then after the was like potential hardness and output. And finally, that the hydroxy groups tend to adopt the system as an P-type, while the epoxy as an N-type. And as we with the oxide coverage, the reactivity of the system takes increase. In the work titled Graphene Nanostructures Functionalization, Hydrogen Bonds and Oxide Coverage, published by Dr. Frias and Dr. Guerrero, they study two materials with the pressure of BD. They determine that the hydroxy groups are stable on the surface of the graphene, meanwhile the epoxy tends to prefer the edges of the system, and also as we increase the epoxy and carbon ratio, the electronic conductivity of the material tends to decrease, which was confirmed with some experimental results of graphene oxide synthesized in the organic materials lab of University of Quindío, represented in the graphene vanguard energy versus the oxygen percentage, in which the experimental data and simulation data have a good correlation. Additionally, the non-covalent interaction indexes were determined to check the presence of the hydrogen bonds that form between the hydroxys that have certain proximity, as we can see in the graphene. we employ the DFT, the functional DVD, using software bus in the supercomputer listed property lab in the cluster of nanoscience and nanomaterial center of Terminado, California. Regarding the model use, the velocity model was selected and based on the previous investigation, the hydrogen superposition must be on the surface of the structure perfectly in the center, while the epoxy on the edges of the system. Additionally, the structure was activated with hydrogen atoms to cut the periodicity of the system since we're dealing with the polycrystalline material. For this investigation, 5 configurations were taken, reciprocity, and then 5, 9, 15, and 16% of oxide coverage, in which were defined certain positions of CO2 to carry out the calculations and obtain the absorption energy. So for now, we're going to focus on the results of the crystalline graphene and the graphene oxide 9% of oxide coverage, which has 3 configurations as we can see here. This is GO1, the CO2 was positioned in the hydrogen sample part. GO2, where the CO2 was positioned in the near the hydrogen sample center, and GO3, where the CO2 located right beside the C4 hydroxyl in the right. And as we can see here in this figure, after the calculations, the CO2 positioning is about 3.52 angstrom of the surface of the crystalline graphene, and then we have the distances that positioning the CO2 from the hydroxyls in each of these positions. The tendency that we attribute to the differences in the electric. In figure GNH, we also can see the molecular electrostatic potential that we use to indicate the reactivity points of the system, knowing some type of interaction between the CO2 and the hydroxyl because of exchanges of the distribution compared to the crystalline graphene. And because of that, so we also obtain the non-polar interaction indexes, checking that there was some interaction of the CO2 molecule with its surroundings. That's why we also calculate the valence charges to calculate or analyze the charge transfer, highlighting, I want to highlight first the GO2, since it was regarding to all the information that we're talking about. They want to keep the best results as we are going to check in table 4. That has the main value for the absorption energy and also has the most charge transfer we can see in this one. So all of this information is in the range of the desorption mechanism, so it could be possible that the adsorption mechanism associated with the carbon capture in the structure of graphene oxide with 9% is, it could be the desorption. Recently, we published these theoretical and experimental results in the journal Scientific Reports, where we use graphene oxide foams that were synthesized in the organic materials lab with this configuration we can see here. We compared with 2 traditional materials for absorption, like SILAR, finding that our system tends to retain the carbon dioxide, and that's why we presented or we proposed an application where, for example, it supports some public areas like traffic lights, or we could measure the CO2 and put our material to try to remove the excess. So now our main goal is to continue with the study of the different, or the other oxidation coverage of the graphene oxide, like 5, 15, and 16%, to identify which of these would be the most suitable for this application. There's also the goal to transform the captured CO2 into oxygen with environmentally friendly processes, as other studies with other greenhouse gas effects, the capture of these ones. So, in conclusion, we have the optimizations of the structure CO2 graphene oxide via the DFT and the molecular electrostatic potential non-covalent interaction indexes and charge transfer were calculated, finding that there is an interaction that will lead to a possible insertion mechanism of the CO2 in the terminal site. Thank you so much. As a reference to NEO is, as you can see in the images, is a region from Colombia, a Cauca region, and for example, if you watch the movie Encanto, Salento, one of the municipalities of NEO, was the inspiration for this movie. This project was partly financed by the project of Galicia, and thank you so much. Do you have any questions? Thank you. Thank you, Erica. Any questions?
So the content of our talk will be the following. First, I will give a brief introduction about the system and about the motivation of our study. Then I will describe some aspects about the computational method we use. Then a description of the system that we study, the results and the description of that, of all the information we have, and finally some conclusions and remarks. So as a brief introduction, in recent years, the high temperature and isotropic antiferromagnets have attracted the interest of experimental and theoretical research group due to their attractive properties. For example, among these properties, we have that these kind of materials have a high perpendicular anisotropy, high thermal stability, and high mean temperature, and a high large spin polarizability. So these facts allow us to speed up the information transmission and the reduction of energy loss. With this in mind, it is possible to think about some outstanding applications such as nanospectronic devices based on this kind of materials. So another application of this kind of materials suggests, for example, the use in hard disks, in magnetic random access memories, in sensors, spin valves, magnetic fluid junctions, low-resistant, magneto-resistant devices, and among some other applications. So among these kind of antiferromagnetic materials, we have a very attractive one, that is the one composed by iridium and manganese. But one bad thing about this material is that iridium is a very expensive material. Actually, it is considered as a critical raw material. This avoids the fact that this material can be applied for some applications because it has a very high cost. So with this in mind, there have been a lot of efforts to explore some possibilities in order to replace the iridium and have some material with its outstanding risk but with a lower cost. So in this way we have that gallium manganese is a very good candidate for substitution this material based on iridium. So on regards this gallium manganese material, we have that it crystallizes in two different phases. The first one is the tetragonal, which shows a ferromagnetic behavior, but we have another one which is very attractive from the scientific point of view, because it is an hexagonal phase and it has a very particular magnetic behavior, because it is an antiferromagnetic, but it is also a triangular antiferromagnetic. I mean, the orientation of magnetic moments lie in the XY plane. So it has a non-collinear antiferromagnetic behavior. Another important aspect of this material is that the manganese atoms which are in this material form a Kagome lattice having gallium atoms in the center of one hexagon. I will show briefly. I will show the structure of this material. So, because of this fact, it is possible to think that this material can be a very good candidate to substitute the iridium manganese material because it shows the similar structure, the Kagome lattice. Some important aspect about this material is that it has been applied, it has been used for some outstanding applications such as magnetic tuning junctions, exchange bias, spin valves. This shows a very large value of exchange bias when it's coupled with a ferromagnetic material, and it has been used in spectronic devices. So with this in mind, which is the motivation of our study? In general, despite this material have too much technological application, it has not been applied, it has not been studied from the theoretical point of view, and there is a lack of studies on regards the surface. The studies has been focused in principle in the body system, but there are not so much studies on regards the surface. So in our study, we want to describe to make a very deep study at the atomic scale. At the atomic scale, to describe the role of each kind of atoms in the stability of the surface. So a brief description of our study is that we have investigated the structural and magnetic properties of this surface by using the first principle calculations based on non-collinear spin polarized density functional theory in order to perform a comprehensive study at atomic scale related with the effect of inducing some vacancies on the surface. And with this, evaluate the role of each kind of atoms located on the surface. So, on regards to the computational methods, we have used the Vienna artificial simulation package, the density functional theory implemented in this code. We have to use the spin orbit coupling effect in order to describe in a correct way the Kagome magnetic arrangement which is observed in this material. We use Planck waves for expansion of the wave functions, Coulomb energy of 680 electron volts. We have used the GGA-PV approximation to model the exchange correlation. For electron-ion interaction, we use Paulsen botellas, and these convergence parameters for each self-consistent cycle. We model the surface by using a 1x1 periodicity supercell consisting of 9 and 10 atomic layers, and finally we include a vacuum space of 15 answers in order to avoid interaction between adjacent periodic systems. And also we model or we sample the neural zones by using this chemical mesh. So this is a description of the whole system. First of all, we wanted to start the ball in order to be sure that our results are trustable to proceed with the construction of the structure. So we were able to reproduce all the lattice parameters as well as all the orientation of magnetic moments from the ball that I'm showing in this video. So this is how the magnetic moments are oriented in the manganese atoms. The gallium atoms have no magnetic moment, but the magnesium atoms have this orientation of magnetic moments. So we were able to reproduce in a good way all the lattice parameters. these two possible kind of systems, which are different each other because of the termination. We have a system with opposite chiralities, and these are both possibilities. In this way, we proceed to view these surfaces. So these are the relaxed structure of our surfaces, so we can see that in general the topmost value atom displays a little bit because of surface effects. So then, on regards to the magnetic properties, we were able to obtain the correct values for magnetic moments, the net magnetic moment per each layer, and it's in good agreement with the reported ones. And also we were able to obtain this very small ferromagnetic contribution of 0.035 magnetons, which is in good agreement with other results. So then we compute the orientations of pristine surfaces, in which we can see that a bit augmentation of the magnitude in the magnetic moments of the atoms located at the topmost layer. This is attributed to surface effects. And for inner layers, we observe that the behavior is very similar, or is basically similar than the bottom. And this is the result for the type 2 surface, which shows a similar behavior. So this is a graph which shows how is the behavior of the magnitude of magnetic moments of each kind of atoms located on the different layers of the surface. So this is basically information that I have mentioned before, in which we have that for inner layers or layers at the middle, the magnitude of magnetic moments is very similar than the ones in the bottom. So then we computed, or we induced the vacancies in the surfaces. First of all, we consider some vacancies of gallium in the second layer, and we observe that when the vacancies induced in the second layer, in both cases, we have a bit distortion of the structure. In the case when the vacancies in the first layer, we don't observe this behavior. So when we use the manganese vacancy, we also observe a bit distortion, but not in the same volume. Case of gallium vacancy. So in both the similar behavior. In general, from this figure, in general, we can see that when the vacancies are induced, there is a big change in the orientation of magnetic moments. However, the ferromagnetic behavior is preserved. So this is observed in both systems. So when we have a vacancy of manganese, the effect is more notorious. This is because the surface of the orientation of magnetic moments is more sensitive when the vacancies are located in the surface. So finally, we compute the surface formation energy in order to determine which structures are the most stable. We use this formula, which suggests that the system is in thermodynamic equilibrium, in order to find which is the most stable system. In this way, for this figure, we can notice that the clean surfaces are the most stable in the whole range of chemical potential, as expected, and then we notice that the systems with the vacancy of manganese are more stable than the ones with the vacancies of gallium. This is because the role of gallium atoms is very important in this system in order to stabilize the surface. So despite the gallium atom is not magnetic, it plays a very, very important role in a way that you remove or you generate some vacancy of this kind of atom, the system loses stability. And that was the main purpose of our study, to determine the role of each kind of atom in this kind of system. So finally, as a conclusion, we have that the manganese gallium surface stabilizes in a Kagome triangular magnetic arrangement. In this kind of material, we have there is a big augmentation in the magnitudes of magnetic moments in the atoms located in the topmost layer. That the system is very sensitive when we use manganese vacancies, and finally surface formation energy suggests that the role of gallium atoms is very important in order to stabilize the system, and the most important part of our study was to determine or was to establish that the gallium manganese, hexagonal gallium manganese, is a very good candidate to replace the manganese iridium material for several applications, which is something very important because this material, the gallium manganese, shows very, very similar properties than the iridium-based system with a very, very lower cost. So this is something very important fact. So finally, I would like to acknowledge Dr. Jonathan Guerrero, Dr. Rodrigo Ponce, Dr. Robotic, because of their very valuable help in order to develop this project. And all the financial support for the grant for this project was gotten from these financial supports coming from this project. So thank you very much. And if you have any question, please, I'm open for questions.
Thank you, Mario. Any question? No? Good.
Hi Mario, I have a quick question.
Yeah.
You cite that these kind of materials have some advantage in comparison with iridium-based materials. Could you explain a little bit more about that?
Some advantage, principal is the cost. I mean, in general, they show very similar characteristics. For example, the orientation of magnetic moments and the magnitude of that magnetic moments. But the main advantage is that the gallium manganese is a cheaper material. We will also find that the orientation of magnetic moments is similar, and some other aspects related with the Hall spin effect and something of this kind of response is very similar. So that is the main advantage. In general, if you compare both systems, you will find that they are very similar, each one from each other. But the cost is very, very low. So this is the main advantage.
Okay. Thank you so much, Mario.
Thank you again, Dr. Mario Galicia. And now we'll continue with the last talk on this program. The next talk is given by Dr. Jonathan Guerrero.
Okay. I'm going to show you
Entonces, ¿no tienes frío? ¿No tienes frío? Sí. Oh, no, güey.
Okay. This morning for meeting. Today I'm a little bit for the bottom. That is inclusion channel that goes the activation for the carbon monoxide to carbon dioxide conversion in the outside. And there are some countries, this will be the outline of the talk. First, I will be creating production to explain a little bit about the research question and why we carbon the calculations. Let me tell you that the calculations are mainly to explain experimental findings of our collaborator here. After that, I'm going to discuss the answers that we reach, and I'll show you the final result. Okay, so carbon monoxide is, you know, this question. It can be smelled, can be heard, and also it can not be stored. So almost 500 deaths happen per year due to carbon poisoning. So check yourself if you have signs of carbon monoxide poisoning, because the main poisoning with carbon monoxide happens indoors. So the leading causes of carbon monoxide poisoning are furnaces, stoves, fireplaces, also water heaters, and one of the most important sources of pollution are the rolling jars. So we are immersed in a carbon monoxide atmosphere. We are covered with oxygen and some other things, and also that is a very interesting fact that men are 2 times more likely to be affected by carbon monoxide poisoning. So in an environment with carbon monoxide, the more likely to be affected would be the man. Okay? So carbon monoxide affects the blood's ability to carry oxygen. So if we breathe carbon monoxide, that will then in our bloodstream. So high concentrations of this carbon monoxide might affect the vision, the ability to concentrate, and also the coordination. Let me tell you that very high concentrations of this carbon monoxide can cause death. For example, here in this table that I found on the internet, you can see the main concentration of 35 parts per million. You will have headache, dizziness, right, with 6 to 8 hours of constant exposure. And that increase, if it increases, it will generate severe effects. For example, here in 6,400 parts per million, it will generate headache, dizziness, in one of the convulsions, and then in the So we need to be really careful when exposed to carbon monoxide and the poison. Okay? Okay, so the carbon monoxide is around the globe, and that is very well known. And here I found in in the page of the NASA Observatory that until September 2022,
Case of value vacancy.
the concentration of carbon monoxide in parts per billion by volume. For example, here the most large concentration is in the South America, right, and Africa, but also the US and somehow Mexico has also among you see in average there are 150 per billion. So there are 150 carbon monoxide molecules per billion of iron molecules. So there is not very much. However, that together with the indoor pollution, it may induce the very process like the ones that I mentioned before, right? The most part of okay, so now I want to explain a little bit about the material that we use. As I mentioned before, this material it was used by our experimental collaborator because the city outside is well known that it serves as a source of oxygen to carry out this reaction in which we turn from carbon monoxide to carbon dioxide, right? Okay, so the structure of this material is easy. It has a fluoride structure and is cubic. You can see the space group. In this structure, the cesium atom has four. It is four floors, and it's surrounded in a horizontal geometry, surrounded by a equivalent oxygen atoms. The oxygen atoms are 2 million, the charge is 2 million, and they form a whole name of about 2.37. Additionally, the oxygen forms let's say that a tetrahedron with the cerium atom nearby in its name. Okay. This structure is before, and the largest parameter is 5.47. Okay, so we use this structure to explain some experimental findings obtained. Now, okay. So we know that city oxide has a large oxygen storage capacity. It has also this is experimental pressure, rapid and relative ability to take and release the oxygen. So somehow it has a good oxygen diffusion. Efficient supporting material for moving metal also. It can work as a supporting material for platinum, palladium, and also gold. Though cerium oxide increases its oxygen uptake and release, and it eliminates the presence of carbon. One drawback of this material is that when in its pristine form, once the reaction happens from carbon monoxide to carbon dioxide, the carbon dioxide gets trapped on the surface, and then it poisons the surface, reducing its capacity to transform carbon monoxide to carbon dioxide. Okay? So, doping is a way to reduce its poison. Okay. About experimental evidence, more experimental evidence from this material More experimental evidence of this material is when it is doped with gallium, reduce the formation of this carbon. That is an experimental part. Also, it increases the oxygen mobility, but they measured that, but they didn't know why. Also, the oxygen explosion is attributed to surface oxygen balance. Okay, that is another experimental fact. Okay, this is presentation. Okay, perfect. Now, here I show the experimental results that they obtained. First, they dope silicon oxide with 0.25% of gallium, or 0.50 and 0.75. So they have three concentrations, and they prove how it is the performance of each concentration in the carbon monoxide oxidation reaction. Also, they use 0.25 gallium impregnation. How do they do that? They just put gallium on the surface of the silver oxide, and then they compare all these materials with the silver oxide. As you can see, the silver oxide is the black line with the black squares, and the conversion from carbon monoxide to carbon dioxide is around 40% of 0.4. But when we include 0.25 gallium percentage, the conversion is almost none. So gallium somehow is increasing a lot the conversion, and that's a question that the experimental colleagues have. Why is doing that? Notice that also 0.50 and 0.75 increase the conversion. They are not as good as the 0.25%. Also 0.25 impregnation right in the surface, it increases the transformation, and that's very interesting part. Okay, so the question is, why is the 0.35 serial sample is the one that has the lowest conversion? Why is that happening? And the other question is there a role of the surface gallium incorporation in the oxidation reaction? Is there any role of the gallium incorporation in the surface? That's the other question. Okay? So, there are two figures that show how is the conversion with and in present and without oxygen protein binders. So, a interesting point here is that even without environmental oxygen, the silver oxide is an oxygen source, and that source is better with gallium. So let's see why. Okay, what do we know from the experiment? The experimental part tells us that gallium atoms incorporate into the surface envelope. They measure that with XPS. Gallium atoms in the core move into the oxygen diffusion. That's an acceleration that, okay, they measure that, but they didn't know why. Surface gallium atoms might promote carbon formation. In this case, vacancies are the ones that they thought that the vacancies are doing the work to obtain the oxygen source for the oxidation. And carbon oxidation reaction happens because that's a part that for sure happens. And also, gallium also recruit this carbon dioxide process. So, well, that we know from experiments, and we answer each question one by one. First, to answer if the gallium atoms incorporate into the surface and oil, we carry out a series of calculations, including gallium in 0.25 on 0.50 and 0.75% in the serial side. So we form three structures. A is 0.25 gallium, B is 0.50 gallium, and C is 0.75 gallium. Notice here that in 0.25 the gallium atoms form like a channel from water to the surface. And okay, in the configuration they try to get together. Right? Okay, so once we have the methods, we compare the stability, and we see from this image, the one at the left in the board, we have here a diagram in which we have gallium conditions on the y-axis and helium conditions on the x-axis. This graph tells us about the stability concerning the quantity of gallium and quantity of helium. For example, in the superior part here, you can see that the pristine structure appears as gallium pool with helium rich condition. But if we reduce the helium condition to pool and also at gallium rich condition, that is these sides, we find the serious exclusion that tells us that gallium might take on helium sides, and it will be exchanged one by one, and that tells us that in fact helium is intercepted by gallium on the bottom, and the same happens on the surface. You can see here the city outside 111 super is the more stable than the one that they have in the experiment. It is also substituted the helium by gallium. So we have for sure gallium on the surface and gallium at the bottom. And in the 0.25% we have this channel-like formation in which the oxygen atom around the gallium atom gets the most weak. So they made gallium D019 box. Let's see that later. Okay, so the other thing is that gallium atoms in the world move into the oxygen diffusion, and how we do that? Okay, since we notice the diffusion channels, we try to diffuse the oxygen atom from one hydrogen site to another in several positions, and we notice that in this image, you are seeing the diffusion value. So the energy that takes to move one oxygen atom from one hydrogen site to another, but in area outside the pristine one, in the 0.25 area value, and also the 0.50. Notice here that as the gallium content decreases, in the first case, we have the largest diffusion value. Also, in the conductivity, we have lowest variable, it is larger than 0.25 K. So the 0.25 case, the diffusion value increases because this diffusion channel of the oxygen is going to the gallium atoms from water to sulfur, and that helps to increase the oxygen level. See here, we will have the diffusion channel, and these oxygen atoms are the ones that diffuse to the sulfur. And also, in the case of oil 50, that happens. Since we have more value, the bonds get somehow stretched and they increase the diffusion value. So, the second question that we have, indeed, gallium atoms improve the oxygen diffusion, but they improve the oxygen diffusion because of the channel light formation. It is a fact that we already report. Also, surface atoms may promote Bacchus connection, and we are talking about surface mathematics. So we answered that question that it was experimental fact, but we answered that putting gallium in the solution and measuring how is the oxygen balance information. For example, in the outside, the oxygen balance information has an energy of 3.64 electrons, while when we have gallium atoms, for example, this blue one, the cyan one, gallium atom, we will move from this position for an oxygen, the oxygen balance will 2.2, and also the oxygen balance information for a cyan oxygen gallium bond, we will move to oxygen, the oxygen balance energy. So, in fact, gallium promotes the balance information, and the balances may serve as oxygen gas, oxygen from the environment, or oxygen that are diffusing from the body to oxidize carbon. Okay, so now, how carbon monoxide happens on surface. Here I show some schemes in which we have, or we explain how the oxidation happens. First, we have balances. As you know, gallium promotes balances. So we have balances. Once we have the balances, the carbon monoxide gets trapped by oxygen. So the oxygen from the body diffuses to the surface, and then the oxygen can react with the carbon monoxide to liberate carbon dioxide. Okay, so we have more vacancies, and the process goes on, in which one oxygen from the body reaches the surface, and the reaction also happens. Here we have the carbon monoxide, and then the oxygen from the surface, and liberate carbon dioxide. And we have vacancies that are induced naturally by the gallium atoms. So once we have oxygen from the environment, that is easier because we will have a competition between the oxygen that comes from the body and the oxygen.
Qué frío sí hay. Qué frío sí hay. Oye, ¿y dónde es que hay ahorita?
No sé, es una plenaria, así que es importante.
O sea, a lo mejor ya que estás haciendo, me dan la mitad de lo y ahí me da un
O sea,
And we are basically trying to address the markets that are basically demanding higher data rates and more processing power, more bandwidth, lower or efficiency, etc. So we are in those markets, and I'm gonna discuss a little bit about that here. Very quickly, once again, Semtech is basically working products in these three main niches. For this presentation in particular, I'm going to be focusing on the product that we developed to address these higher bandwidth needs, right? It's basically the astonishing growth in data traffic, what's been placing unprecedented demands on telecommunication infrastructure, networks, and data centers, right? Just to put things in perspective, probably you have heard about these new super large hyperscale data centers that are being developed around the world, right? Behind this is obviously this artificial intelligence, ChatGPT, huge data centers to exchange information coming from IoT, advanced cellular networks, and so forth, right? Just to give an idea, these very large data centers that are being developed today, some of them are like at 50 hectares, right? It's super huge, massive computational facilities that require a lot of interconnections, very fast, very low power. So we're basically going to be discussing projects related to that in this presentation. So I'm going to start with the CMOS technology process, probably the most well-known process nowadays, right? It's been the workhorse for electronics industry for decades, right? And it has some characteristics. Once again, I'm going to try to go quickly through this. We have some questions there I'm going to be happy to answer. But basically, the main characteristic is the low power consumption, particularly static power consumption for switches. When the CMOS, CMOS is a combination of a PMOS and an NMOS transistor, right? And this is what gave birth to these very high efficient switches, right? So for digital logic or for digital circuits, it's been really the best technology in terms of power and speed. Is highly scalable technology, silicon-based, etc. So had many advantages. And because of that, as more and more processes and circuits and things were digitized, this was a technology of choice, which resulted in economies of scale, right? Basically, reducing the manufacturing cost, developing a huge infrastructure behind it to support it. So that's why basically it's been used. However, obviously, since this was really the technology of choice for all the digital functions, but still, we needed to implement. We still need to implement some functionality in the analog domain. So we were kind of forced, in order to have everything on a single chip and leveraging these low-cost manufacturing processes, we needed to include some analog, right? So this process has some tweaks for introducing this analog functionality and even RF, as I'm going to show in the next slide, I think. Well, very quickly, reviewing the process. This is, as I was saying, we can have P-type or N-type or P-type transistors. Everything is developed on silicon. We start from a silicon substrate. Silicon, is the most abundant material and relatively inexpensive to fabricate the wafers. This is basically the structure by a conventional CMOS technology, where we can have some implants, dopants with N plus or P plus dopants, and we can have welds producing this in order to fabricate the PMOS transistor or the NMOS transistor. We can have metallization. We can actually one of the main advantages of the traditional CMOS, or actually pretty much any silicon-based process, is that we can have a native oxide, right? The silicon dioxide, very easy to grow on top of the surface, and the entire process, as you may know, relies on a very sophisticated lithographic process, right? In which we can be adding and removing materials layer by layer, and we can add dopants and basically change the characteristics a little bit of the semiconductor in order to fabricate these devices. So we have the photoresist that we use to mask the areas of the wafer where we're going to be applying some of this processing. We have etching, which is dry or wet etching to remove materials as part of the fabrication process. And we can have different kinds of doping methodologies, right? One of them is ion implantation, which is highly anisotropic, and thermal diffusion of dopants, right, which will be isotropic. We can also deposit materials using different methods: chemical vapor deposition, physical vapor deposition, and others. Annealing, which is basically a heat treatment that basically is going to help us make more homogeneous the dopant profile in general of the area which has been exposed to the doping. And metallization, in modern technologies, we can actually have 10 or more layers of metals for the interconnect. Now we have such a high density of devices in modern technologies down in the substrate that we need to have many possible ways to interconnect them, right? Literally, we have hundreds of millions, or in some cases even billions of transistors that we need to interconnect, right? Now later on, the problem is the input-output capability or area to take information in and out. Okay, so this, as I was saying, this is the traditional or the conventional standard CMOS process. There is also a twin tube well technology in which we can actually kind of isolate the PMOS and the NMOS transistors. Instead of having just an N well area, we can also add a P well and have the two different transistors. This technology, I think, is not that common anymore because it's being replaced. Let me switch to the next slide, please. For some reason, this is not working. No, I think you went too fast, no? One before? No, before? Yeah, this is the one, okay. So I was saying, okay, so the conventional CMOS process, already explained or discussed a little bit on the surface the characteristics. One of the things that we can encounter in this traditional structure, which is coming from the previous slide, is that we have some intentional bipolar transistors get formed, right, by the combination of these P and N junctions as a parasitic, right? So this is not that we wanted to build this bipolar transistor, we wanted to build this NMOS and PMOS transistors, but we get this as a parasitic, right? And this is forming an unintended circuit that could cause a phenomenon called latch-up, right? Which is basically, under certain conditions, these transistors will turn on, and then we will have current flowing through them, right? And it's not only a problem of power dissipation, it will actually damage the circuit. So this is, latch-up is kind of a challenge sometimes when we're designing transistors using this process. So look at this once again, where we're just stacking different layers of materials in order to build some devices, and then we want to design some circuits using those devices, just combining these materials. But then we have these unintended devices or unintended elements there. That's why there's other modifications to the conventional CMOS process, and then we have SOI CMOS, in which the regular substrate, on top of the regular surface there is a layer of silicon dioxide grown on top. And this is really helpful. Sorry, really helpful to isolate the transistors, right? So with this we can completely eliminate the latch up. We have a reduced leakage current. It's more power efficient, reduced junction capacitance. So it has a number of benefits. There is, as you may expect, nothing comes for free. It is more expensive, right? And so in some cases, this is why industry insists in keep using conventional CMOS. And in conventional CMOS, as I mentioned a little bit before, we have added some passive elements to be able to also implement and introduce analog circuits along with the digital circuitry. And then we have specialty nodes, including RF CMOS, in which we can actually have inductors, right? Metal inductors, and the models for them in order to have resonant circuits and filters and so forth that we can use in RF, in radio frequency. All right. So okay, this is basically the basic technology, the most, not basic because actually fairly advanced, but I would say the most widely known technology used in the industry, right? And a quick example for this is this project that we in Semtec. Once again, my team in Aguascalientes has been working on this project. This is a 65 nanometer CMOS process, a standard process. And this is basically a product which is a laser driver amplifier that works up to 10 gigabits per second. So why is that we use CMOS for this product? Okay, one of the reasons is always, well, one of the main reasons is we needed to have a product that was competitive in the market, and price is paramount. So we needed to find a relatively inexpensive process, relatively speaking, obviously, right? So a CMOS process was most fit for this instead of going to more to other processes that are going to be shown here in this presentation. The other reason is this project in particular included some control logic and an A to D converter. So that's something that is very suitable to be implemented in CMOS CMOS logic, CMOS transistors. But also we needed we need this to operate relatively fast. So that's why we went into the 65 nanometer nodes, where the transistors actually are very fast. The switching speeds are relatively low, or say very low. So we can have a high speed digital functionality and be able to drive these lasers. And I told you I was going to be talking about products that have to do with these data centers and high speed and all these big data and artificial intelligence world that we're living in, right? So these, right, where we're transmitting communication data. Okay, so this is the example and the reason why we use this technology in particular. I'm going to skip this one. Then we have another technology, which is BiCMOS. So BiCMOS, as the name implies, is a technology, a fabrication process which allows to actually build or combine the bipolar transistors, bipolar junction transistors, and CMOS transistors. So with this, we will have the benefits of the two different technologies, right? It's basically we have CMOS transistors for logic, and then we can have BJT transistors for amplifiers in general, right? So we can benefit from the high input impedance of the MOSFET technology, and the high current capability and low output impedance of the BJTs. As you can see, the structure is once again tweaking the process. It's going to be adding some different layers and also some different doping needles to the material in order to be able to incorporate a BJT, a native BJT, in addition to the regular PMOS and NMOS. So as you can see on top of the P substrate, OPP or N substrate, this is the most common one. We can grow an epitaxial layer, and then over there we can have the same structure that you saw in the previous slide for the CMOS technology, the N well for the PMOS transistors, and the two diffusion areas to form the drain and the source of the NMOS transistor. But here is where we are incorporating an intentional or intended BJT, right? And as you can see, first we need to have an N plus void layer. This N well will be very similar to this one, except that it's kind of a U. There is some etching and special anisotropic process to build these wells. And then we have a P-base, which is slightly doped, not slightly doped, but doped to the right concentration for the BJT to have a high gain, right? High forward gain. And then basically the structure, we can see we have the base emitter junction, and then the collector, which is going to be actually collecting all the carriers, minority carriers coming from this junction, and we have the avalanche effect that we only have in the BJT. So this is one suite for mixed signal applications when we have analog and digital circuits, right? And when we actually need to drive relatively high currents, input-output circuits, etc. So this is basically what we have. The drawbacks of this technology, as you can expect, we have additional fabrication steps, right? And additional layers for fine-tuning both the bipolar and the BJT transistors in order for them to be optimal, right? And this increasing complexity translates once again in manufacturing cost. And as I was telling you before, this is a very one of the main parameters that drive the decision of what we're going to be using to design circuits, commercially speaking, has to do with cost. Exactly we're designing military applications or some other things, but in general, nobody wants to buy a more expensive phone than another one, or a more expensive television or stuff like that, right? So this is very important. Cost is very important. This is an implementation of a circuit that we have also once again developed in Semtech. This is a load protection switch, which is designed in 180 nanometer by CMOS process. It's basically, we call it hot switch, it's kind of a commercial name, but it's basically a circuit which is going to disconnect the load from the supply as a protection element, right? It's an active element. Traditional circuitry to do this is a TVS, a transient voltage suppression diode. And basically, in a passive way, basically this absorbs the current going into the load that goes through here. Still, it's less power efficiency by far than completely disconnecting the load, right? So with this, in this circuit, we have a temperature sensor and once again some control logic to disconnect, etc. Why do we use a BiCMOS process in this case? Well, I think it will be pretty obvious that we need high voltage and high current transistors in order to drive the loads. So bipolar is needed for that purpose, right? So that's what we needed, the bipolar. And the CMOS part has to do with the control, right? Much better implemented with MOSFETs. So this is an example how we're using different technologies for different purposes. The third technology I want to discuss here is the SIGI, or silicon germanium process, right? This is a high-speed technology because, first of all, as you can see, this is a compound, right? Silicon and germanium. Silicon, or germanium has a lower band gap than silicon. Right? So it's a faster switching, higher mobility of carriers. And the interesting thing here is that we can build heterogeneous bipolar transistors, right? Which is, as you can see, basically a very similar structure. It's a bipolar transistor. You have the emitter base junction and then the collector surrounding this junction. The difference here is that the base, or the emitter base junction, is using a different material. That's what's heterogeneous, right? A heterogeneous transistor, and pretty much works the same as a bipolar. Is faster, and the fact that we can manufacture defect-free silicon germanium lattice on top of the silicon substrate yields or results in some benefits. Particularly, this is much more immune to noise. It intrinsically produces less noise, 1/f noise, than other the traditional CMOS technology. So normally we use this technology when we need fast switching. So in some applications, in particular radio frequency in some analog, we need very high speed. We use silicon germanium. This is another view of the process. So we can have it on the same die, on the same monolithic structure. We can have PMOS transistor, NMOS transistor, and our HPT, the silicon germanium, right? So this transistor in particular is better than the traditional BJT, right? In terms of the speed, higher forward gain, lower reverse gain, and what I was saying, right? Lower RF noise and low 1 over F noise, intrinsically produced by the system, right? Silicon germanium provides the potential to integrate CMOS logic and HPTs on a single chip, making it ideal for mixed signal circuits. What I was saying, mixed signal is analog and digital combined together. We'll have all the functionality there. We can also trade, since this is faster, sometimes not that we need to operate faster, but we save power, right, in comparison to conventional CMOS or even by CMOS. And there are some advances, recent advancements in CD in such a way that they are fine-tuning the technology to have better quality passive elements, resistors, capacitors, and so forth, to the point that CD is is more and more replacing gallium arsenide, which is another technology in applications, circuit applications. One of the products that we have developed using CD process is this VCSEL driver in 180 nanometer CD by CMOS. A VCSEL driver is basically, I think VCSEL is a vertical cavity surface emitting laser, right? It's basically a diode. Essentially, it's a diode. Once again, using different material, we can have a diode that emits light. It's a laser. But this one in particular emits the light vertically or perpendicular to the surface of the wafer. And it's used in many optical applications for data centers, right? Where we're transmitting communication there. And because of the speed that we needed there, we needed HPTs. Right? So this was the technology of choice for this particular application. For that reason. Then the fifth process that I want to discuss here is gallium arsenide, or gas. This is a very specialty process, kind of expensive, as I'm going to mention. And this technology is known for its high electromobility. First of all, gallium arsenide is a 3,5 material compound, right? It has a direct band gap. So it's not really a silicon-based material, right? Or not in the sense that it is based on the same technology that we use to fabricate CMOS and BiCMOS and even CD. So it requires a different manufacturing technology. So in these cases, in this particular case, what we have as a new device in comparison to the previous processes is that we can introduce the MESFET. The MESFET is very similar to a MOSFET, except that we don't have the insulating layer between the gate and the channel of the transistor, right? So we're kind of forming a Schottky union there, right, as you can see there. So the advantages is higher electromobility and velocity, naturally yielding higher frequencies of operation. This is very important. In gas, we can have a very high Q passive components, right? That's what I was also mentioning. The recent advancements in CD are kind of a focus on improving the quality of the passives, and therefore replacing this technology in some applications, not in all of them, but in many. Less intrinsic noise, what I was mentioning. The fact that they have the gallium arsenide has a direct band gap results in more resistance to radiation damage, and therefore one of the important niches of application, you will see these a lot in military applications for radars and space applications, etc. So we are using for radars and some microwave applications. Obviously, these are high voltage devices due to the manufacturing. And naturally, I think there were some talks already on photovoltaic cells, right? So gallium arsenide is one of these compounds also used for that matter, and also for some optical applications as well. And what is the drawback? Well, the main drawback is once again cost. You know, the first slide, or the first technology that I was discussing was CMOS. It's the workhorse of the electronic industry. There is the volumes in which we're fabricating CMOS lowers the total cost, right? And we have a lot of facilities for that. It's silicon based, etc. So the tools, all the ecosystem that is needed to get the systems. I mean, from the design tools, include software, the wafers, the actual fabs, the factories where we can manufacture this, etc. Make together an economy of scale, right? So, for instance, seeing what is kind of a piggybacking on the existing infrastructure for CMOS, right? But it's not the case with gas. You know, gas requires a different infrastructure, and therefore it's a very expensive technology in comparison. This is an example of a product that we have designed using gallium arsenide technology. In this particular case, it's an EML driver. You know, the previous one was a pixel driver, and this is a EML. EML is electro-absorption modulated laser. It's a different kind of laser. Normally, when we have lasers for electro-optical applications and data communications, there is also everything started with the direct modulated laser, right? Where we can actually turn the light source on and off to get ones and zeros, right? But this is affecting somehow the characteristics of the laser source itself. So in these cases, the modulation happens after the laser. So it's modulated by an electro-absorption mechanism. And this is, it turns into less dispersion, and we can have very long reach for these lasers, so up to 40 kilometers reaching this particular product, versus directly modulated laser, which is maximum 10 kilometers or so. So this is a different laser than the previous one, right? It requires, once again, very high speed to do the EML, and in this case we are working at 100 G per lambda frequency rate. Well, by the way, this is kind of the whole module, right? Where we can have electrical signal coming in and optical signal coming out, and vice versa. Let's get this one too. Then we have FinFET process, right? FinFET process is somehow the latest, the greatest evolution of the CMOS technology as of today. It's really, FinFET transistor is really a MOSFET, you know, they belong to the same family of transistors. The problem is, you know, CMOS has been relying on shrinking every generation, right? Which means we have smaller and smaller transistors every time. But then when we have reached certain dimensions, we started having some funny or unexpected performance of the transistor, because we're encountering some, actually even some quantum mechanic effects, and also some of them is actually due to the what's called the short channel effect. Let me go back to show you. For instance, the drain and the source are so close to each other, the gate is so small that we can have, the transistor is no longer behaving according to the equation that we use for design. Right? We have the short channel effects, and it's very easy to have leakage currents and so forth and so forth. So we needed a better way to control the channel. It's not the only challenge, but I would say it's the main one that we can use to explain the FinFET process, right? So let's say this is the traditional planar technology. We have the drain and this is the previous slides were showing the transistor from here. Sorry, from this area, right? So this is like turned 90 degrees. So we have the drain in this side, the source here, and then we have the channel, right? And this is the gate that controls the flow of electrons underneath. But this is when we continue shrinking and decreasing the geometry of the transistor, we have this problem with controlling the flow of current. So once again, this is a very interesting idea that was developed by the different proposals that happened. First they come up with an idea for twin gate. They had a gate underneath and a gate on top and so forth. But in the end, this is This is basically what's commercially more successful. And it has to do with development of materials, thin film depositions, etc. So in this case, the innovation was the structure of the transistor. This is still a MOSFET, works like a MOSFET, we use the same equations, but physically the implementation is different. So the idea here was to take the drain and source out of the surface. It's no longer planar, it's a 3D structure. That's what's called a fin. And then the gate is built on top. So by doing this, we're effectively increasing the length of the gate, right? Because from here to here, whatever the dimension is, this is the length of the gate. But now we have from here to here, then it turns, and then pulls down. So we're effectively increasing the gate length, but also we're controlling the channel from one side, from the top, and from the other side. So we have a much better control of the current flow. So it's just the evolution of the traditional planar transistor into a three-dimensional structure. Very interesting advancements of materials, the manufacturing processes behind this technology. In the end, it works like a MOSFET, right? But because of this innovation, we have been able to continue shrinking the size of the transistors. The most modern processes that we're using today is 3 nanometers, right? So all these things all these phenomena started to happen. It wasn't really whatever we had in simulations with the actual test chips that we were fabricating, starting by about 28 nanometers, maybe even from 40 nanometers to 32. So it wasn't going to be possible to keep shrinking the transistor going this path. This was an important innovation in the process, in the manufacturing process, in materials, in processing, and then we can have transistors. After 28, we had 20 nanometer, then more or less 16 nanometer, then it shrank to 12, to 10, to 7 nanometers, to 5 nanometers. The most advanced processes today are using 3 nanometers. So it's really incredible. So, let's see, right? FinFET became the replacement of MOSFET in a small geometry. It's still a MOSFET, it's just a different structure. Actually, this is, for instance, how we can even stack transistors together, right? Remember, when we want to have a larger transistor, we normally use a bit-sized transistor and put them in parallel. It's more efficient in terms of physical layout, area, and also to preserve the characteristics of the transistor. You know, it's not the same having a very big transistor than many smaller transistors put together. So this is how we can easily put, for instance, in this case, 3 transistors together. The same gate, drain in one side, source in the other side, one gate. So it's very easy to have to make bigger transistors out of this geometry or this structure. So we have lower power consumption because we have more control over the gate, less leakage current, lower operating voltage, super small features, right? So we can, with small voltage, we can turn in and off the channels. Very low static current leakage and very high compactness, right? This is where we're having the latest generation memories and microprocessors, right? Super high density of transistors. The drawbacks or the challenges is obviously this is a much more complex fabrication process. It's a 3D structure, super expensive. Just to give you an idea, probably 7 nanometer process, just the masks for the lithographic process should be around $10 million also, just the masks, right? So unless we have a very large volume of chips to fabricate, there's no point in going into these technologies, right? And there is also interesting things that happen when we move into these very advanced small geometry nodes. We're not allowed to put like design transistors any size we want, right? Because once again, obviously the process is very strict. You know, there's just so much we can do at these dimensions, right? And how many transistors we can put together, etc. So the sizes of the transistors that we can actually fabricate, it's discretized, right? So we can have just a number of dimensions that we can use, and from there on we can design some transistors or not. So this turns into physical implementation. Or physical implementation process design limitations. Some of the designers in the past that were not used to this technology, they say they put whatever dimension or more or less whatever dimension they want to match or to obtain the transconductance that they need and whatever of the impedance and so forth. But it happens to be that we cannot fabricate this. So when we come to physical implementation, then we have to be aware more and more aware of the process behind the circuit itself. So how we're going to be building and fabricating those transistors, so that we have to take that into consideration from the design. And obviously larger parasitics. Imagine we have things just a few nanometers apart from each other. So the parasitics are huge, right? Parasitic capacitances in particular, which is what is killing the speed in some cases. So some challenges there, right? We have very fast switches with very high parasitic capacitance. So on one hand we have high frequency operation, but the capacitance is acting like a low pass filter. So then what we can do about it? So there are some other ideas and some other innovations that are happening or occurring at the same time in order to try to improve this. One of them is the following course that I'm going to show you. But coming down to an example, this is a project that we are, it's actually even currently under development. We have a team of about 20 people working on this. And because of the speed that we needed there, we needed HPTs. It's a 7 nanometer process. And this is what we call a tri-edge platform. It's basically a system that we're using for the application goes into data centers once again. It's a CDR, plug and data recovery system, which includes a transimpedance amplifier and a driver. So basically this is like the whole module to code information and recover information out of a data stream, which might be translated first from optical into electrical, right? So for that purpose, we are using a PAM4 element, but I'm not going to get into that. But this, what you can see here is we're getting into the 400 gigabit per second speeds for these very advanced data centers, and this is what we're using for that. So I was talking about next generation technologies and what's at the frontier right now of this commercially speaking. Obviously in the labs and the universities, research centers, they are exploring other avenues as well. But the frontier in industry is silicon photonics. I was telling you, okay, we can have transistor switching very fast, but now the problem is how to move the information in and out of those transistors, right? Or out, in and out of those circuits. So in silicon photonics, the idea comes from the fact that somebody said, okay, you know, it's instead of moving electrons, you know, to represent information, we can move photons. So we're going to use light instead of electricity. This is a concept that's been there for about already 20 years or so, but it's been really, it's been growing really fast, and it translated from concept into practical projects in about 10, 15 years. And here's how it works, right? Normally, when we want to use light instead of electricity, we can use either compound elements, which we call 3 and 5 materials, which once again gallium arsenide I was discussing a moment ago, or indium phosphide, or we can persist and try to go into silicon because of the economies of scale that I already discussed, right? And this is what's called silicon photonics, which could use silicon or silicon nitride as a material. Okay, so silicon photonics, the idea is that we want to leverage these billions of dollars and years of R&D investment that has been implemented or developed to have the integrated circuits, right? A small node, low-cost systems integration, mature design tools, testing, everything. So that's why we're trying to push light into silicon, when perhaps silicon is not the best material to move light. But there is a reason behind why we're pushing towards this. So this is perfectly suited for data centers. Once again, applications requiring higher bandwidth. Other applications include all this infrastructure for 5G, 5G cellular networks. You know, you have these towers and base stations, but everything in the end has to be connected through optical fibers, kilometers, and blah, blah, blah. And in the end, everything goes back into a big data center somewhere in the world. For this long-haul optical interconnects, what I was saying, LiDAR, which as you know is the new technology for measuring, ranging solutions. It has a lot of applications in smart automobiles and so forth, right? Biosensors, artificial intelligence high performance, and even quantum computing. Let me go back to this. This is very interesting how these are actually scanning electron microscope images of actual circuits, right? And the concepts are very simple in principle, right? How we can manipulate light by just means of interfering with each other, right? We're using optical properties rather than electrical properties in this case, right? So first, this is the grating couplers, how we can introduce the laser beam into the circuit. By having these different gratings, we can, let's say, filter out some different wavelengths and get just the wavelength or the channel that we want into the circuit. We have a structure like this, which is a ring resonator, right? Which can cause a positive feedback or a resonator at certain wavelengths, just by means of having the right wavelength of light there, right? Mach-Zehnder interferometers, right? We can light where light can interfere more destructively, so we can have zeros and ones. And or in this case, different kinds of interferometers, and we can combine light easily, and so forth, right? So it's very basic structures. These are passive elements, right? So basically, with no extra power needs to be added into the circuit. In this case, in this silicon photonics, we just basically have waveguides made out of silicon, as I'm going to show. And when light is passing through these elements, it's getting actually affected somehow, right? By changing the phase of the light, the polarization, by interfering some or other way we do the processing. So we can modulate light or we do modulate information entirely in the optical domain without extra power. So how do we do that? This is the structure of a waveguide, which is this is the equivalent of an optical fiber, but implemented in silicon photonics process. The principle is, we can have silicon and then lyocide or a different material on top and underneath, and because of the different gradient or different reflection index, we can have the light bouncing there, just like an optical fiber somehow, right? Obviously, depends on the wavelength that we're going to be using. The material is going to be reflective or not. So that's why we have some limitations. Here, we normally work on more or less in the infrared portion of the spectrum for silicon photonics in these applications. So this is basically once in the structure. We use the silicon nitride layer and then silicon dioxide and blah, blah, blah. So this is basically a waveguide. And we can have all these elements that I was mentioning implemented along with the circuit. We have splitters, couplers, gratings, etc. And if we need active elements such as the laser source or photodetectors, etc., then we have to rely on these 3,5 compounds, right? CD or gallium arsenide or CD or indium phosphide modulators. So this is what you see in these orange phosphide active elements, and what you see in blue is passive optical processing in silicon photonics. So that means we need to have a way to be able to integrate and package the two technologies together. These are different substrates. So naturally, this is a little bit expensive. How the light is injected into the system? Well, the most straightforward part is, okay, we have an external laser, and all the heat and all the power goes out of the chip, and we inject this into the chip by using very small optical fibers, as I'm going to show you later, or these grating structures that I was mentioning. This is externalized by the grating and direct attached by having a very fine super micron size optical fibers coming into the chip. Or finally, ideally, we wanted to have on-chip laser diodes, right? But more expensive, not as efficient as we want them to be yet, but technology keeps evolving. All this is happening with this development and research that is being done in materials, which is the topic of this seminar or this event as a whole. What I was telling you, packaging, it's super important, right? Because we are introducing many different technologies. So the advancements that are enabling the existing silicon photonics application today has a lot to do with this. It's very challenging to be able to align the optical fibers, imagine coming into the chip, then being able to guide these light beams through the chip and having all these being filtered, being modulated, etc., and finally being converted back into electricity and having some process on top, etc., right? And by the way, I didn't mention this, as I said, we have limited time, and this is not exactly about circuits, but it's very interesting when we have the, let me go back, one of these structures, for instance, a Mach secondary interferometer, we can have a PN junction in one of these branches, and we can then electrically change or affect the amount of carriers that are accumulated here, and this is introducing delays, right? The light is not going to flow the same in this branch than in this other one. If this one is subject to an electrical alteration, so this is how we modulate as well. So the external circuit we can modulate. Right? So this is really interesting, and there are many possible applications for this, as you may imagine. Right? Imagine we can do a lot of processing at the speed of light, very much, right? Without the need to convert into electrical. Obviously, down the road, our computers are still electrical, but not necessarily for long. There are already some research and some experiments about being able to have the equivalent digital gates in the optical domain. Ones or zeros for that matter, and imagine that we have entirely optical computers, right? And the interesting thing, once again, this is more and more trying to be implemented, leveraging the existing silicon processes. This is what we have done in Centec. We have been working on this for several years. We have been working closely with the foundries. The foundries are basically the companies that manufacture these things and are experimenting with the different materials and different ways to do it. So we need to be working very closely with them because this is a highly experimental field, right? A lot of trial and error, I have to admit. What we're working on is providing a full chipset solution for 800 gigabit per second application. This is twice as much as we were mentioning a moment ago. So we are getting into the terabit per second domain. Right? This is the next latest generation data trafficking. We do this with conventional circuits. It's a lot of heat. It's very complicated. So when we move into the optical domain, we can have some advantages. These are some examples, actual examples of what we have developed in Centec. I'll tell you some history. We started in 2015. This is a continuous wave laser that we were injecting into the chip and then doing some little bit of processing there, combining the light, right? This is a little bit more sophisticated circuit, or it's actually part of this, where we have these silicon grooves. It's actually like some tunnels, some cavities we fabricate on the surface of the wafer, and this is where the optical fibers connect into the chip. And then we have some Mach sender interferometers to do the modulation in the optical domain rather than in the electrical domain. This is 2017, a more advanced version of this chip, working at 25 gig Mach sender interferometer or modulator. This is the speed at which we are modulating. But the bandwidth of this thing, when we have light, the bandwidth will be up to 50 gigahertz or so, 30 gigahertz easily, because we're using light now. So we can have many multiple channels modulated at 25 gig per second, and then we combine them. It's really mind-blowing what we can do with these things. This is part of the latest things that we're doing in Centec. You can see this is the optical fiber coming into the chip. The alignment has to be very precise. Then we do all the processing. And this is the final product, everything integrated as I was mentioning. It has to be, not all of this is ours, right? I mean, what we're doing is just a portion of this whole thing. We are working in the silicon photonics part, but it gets integrated. It's a 7 nanometer process, and this is to have this 800 gigabit per second circuits. These are some of the experimental results we have had there. This is a 4-level signal, 100 gig PAM. So in each signal, because it has 4 levels, we are encoding 2 bits, right? So it is 200 gigabits per second, 4 channels of this, 100 gigabits. And as I was telling you, the minus 3 dB frequency of this system is about 35 gigahertz, right? So it's a super high speed possibilities that we can have there. I was reading recently that some people is actually wanting, there are some sort of quantum computation is already a little bit outside of the scope of this talk, but quantum computing relies on the quantum state of an electron, right? The spin or something else. It has to be at very low temperatures, like cryogenic temperatures, in order not to disturb the quantum state. So you need to have a huge device just to pull it down, right? To preserve electromagnetic fields and so forth, in order to have it cooled enough, the electron not disturbed. So now they are doing research. Once again, why is that real system using electrons? We can use photons instead. And for that matter, you don't need to be in cryogenic temperatures. And so they are using already some silicon photonics technologies, but to have quantum computing. So it's a very, very interesting thing as well. And in this case, so they are working with the polarization of the light. So, conclusions. There is very important to maintain this continuous research and advancements in materials and microfabrication processes to enable technologies that define the modern society, the modern technology that we use. At the bottom is this research in semiconductors and materials. So there is a plethora of alternatives, namely substrates, compound material, film deposition techniques, etc., with unique characteristics, each one of them, that can address the trade-offs and requirements of different products and applications. As you can see, there are many options. All of them have their merits, and we need to be able to pick the right one for the application that we need. So it's very important there is continued research on this matter. So next generation processes also need advanced modeling and analysis tools along with in-design awareness of physical implementation. Right? There's a new paradigm for integrated circuit designers and engineers, as I was saying. We have to be more and more aware of the actual manufacturing process underneath. The more we understand the physics and the manufacturing process, the better the design is going to be. And obviously the analysis tools and simulations have to catch up. Right? We need to have good models for the technology in order to be able to design properly. The advanced nodes will not only rely on geometry scaling. There's so much we can. This has been said for 50 years or so or more, right? That they cannot continue scaling. It goes on and goes on. But we're seeing there is a limit to how small we can get. And one example of how we can do innovation or get better performance without further scaling is this 3D structure of the FinFET and silicon photonics, exploring with different compound materials and so forth. Successful innovations will be those that can build on top of existing manufacturing infrastructure, right? The silicon-based economies of the scale. As I said, there is a huge industry behind it, right? It has to be mass volume, so very high volumes or mass production in order to make cost sense. So the more the new technologies can leverage or piggyback on the existing infrastructure, the better. And silicon photonics offers many opportunities, but the manufacturing process needs more development. This is still a nearly fairly new technology. So maturity and standardization is needed in order to fulfill its promises. Everything I was mentioning about optical computing and quantum computing and so forth. When I was putting all this material together, and I couldn't but reflect on the fact that at the bottom of all these technologies that we use every day, almost inadvertently, there's basically some semiconductor materials stacked together, right? Moving electrons or affecting the movement of electrons or photons somehow. And this is what enables cellular, internet, artificial intelligence, sending pictures, whatever, In the end, it's really amazing. It's just some semiconductor crystals put together in a specific way that makes possible to have these modern technologies that we enjoy every day without realizing. So thank you so much. This is my presentation. If you have any questions, I have to answer.
Bueno, se acabó esto. Vamos a ir a un lunch time. A ver si hay comida. Ojalá sí. tengo mi café.
¿Qué pasa? ¿Qué me
Sí.
voy a tirar este con...
Ah.
Siempre que me enseñas cómo me regreso el camión para allá.
¿Qué onda? ¿Qué tal descansaste?
Me grabaste conmigo.
Fue bien gracioso porque Eusebio estaba buscando látex en su iPad.
¿Estaba qué?
Buscando látex en su iPad. Y de la nada le salió un juego de, no sé, un juego bien raro. Y volteó para enseñártelo y volteó y estabas dormido.
Me grabaste.
Ahí fue cuando nos dimos cuenta de que estabas dormido. Y ya sacó la foto.
No sé ni cómo pasó la verdad.
¿Cómo te despertaste? ¿Te escuchaste algo o qué?
No sé. De repente me regresé en una conciencia y dije, seguimos donde mismo. Pero no, me enviaste, no sé quién me enseñó la foto. Pero me la enseñaron y dije, no mames, que me dormí.
¿Hablar con la mano? Tengo las manos con el mismo tamaño.
Al baño, al baño. ¿Qué onda?
¿Qué vamos a hacer?
Me imagino que formarnos para la comida o qué.
¿Graba para tu blog?
¿Estás grabando?
¿Estás grabando?
¿Nos vamos a formar o vamos a ir a otro lado? ¡Hala!
¡Ah, la verga!
Como pueden ver, en la filita. ¿Qué vamos a hacer? Porque si nos vamos a formar, pues de una vez.
No me voy a formar.
Entonces, ¿dónde vamos a comer?
Mucha comida. ¿Quieren formar? Se va a pensar media hora de aquí.
¿En la cantada de comida?
Sí, güey.
Buena.
Aquí va a la comida basura. Hay comida también.
Entonces.
Está bien rica.
Comida decente, güey.
Hay puestos de gorditas, ¿no? Aquí enfrente. Perfecto, pues soy mero.
Pues vamos, entonces.
¿Por qué? Así siempre ha sido. Sí, pero ¿por qué, güey? No. Es la primera vez que hablo bien con él y... ¿Qué pasó? Estamos así nomás. Espérame, déjame te conozco más que hasta me chingan.
A ver, con permiso.
Ya no la vi, ¿lo vi ahora?
Ay. Me dio mucha ansiedad de estar encerrado, así que me vine. No sé qué quieren hacer, no sé si quieren ir a comer o ya con ese elote que agarraron la hacen. Si la hacen con eso, supongo que yo iría a comer a otra cosa, porque no se me antoja un elote. Voy a hablar con ellos, supongo. Creo que voy a revisar mi moto. Me estacioné acá por este lado y no he visto que corro bien.
Te van a formar desde la prepa.
No, ahí está bien. Me está dando el sol con todo. Pero bueno, ahora como mejor me estaciono lo de la casita. Ese carro, bueno, muy suave. Voy a ver qué onda. Si siguen ahí, sí siguen ahí, no sé qué piensan hacer. Por lo menos bien, aquí no sé si estén todos. Perdón. Hola, volví. ¿Vamos a hacer algo? ¿O qué?
Pero estos están muy buenos.
No. ¿Qué le pasó a ese bien? ¿Qué le pasó a ese bien?
No sé dónde se fue.
Bueno, pues visto lo visto, se van a alimentar de lotes. No estoy dispuesto a formarme, creo que sería una pérdida de tiempo, así que a lo mejor voy a caminar por acá a ver si encuentro algo como tranca. Si no, de última también traigo fruta y ya con eso puedo aguantar un ratillo. Mira, están saliendo los de la prepa. ¿Qué hora son? ¿Como 9:30? ¿Qué? Son las 2 ya. Se tarde rápido. Considerando que llegué a las 10 de aquí. Con todos estos de la prepa me da bueno, pero esperaba que estos cortinas estuvieran abiertos al menos, pero aparentemente no. Porque están puestos los precios. Yo creo que sí. Iré a checar. Ay, un metro. No debe pasar ahí. Sorry. Parece que hay. Buenas.
Muy buenas que estamos, ¿o qué?
Bueno, ya estuvo. Fue medio chistoso porque el que estaba antes de mí quiso pagarles por uno de 200 y ellas no tenían cambio, me imagino, o no es suficiente. Y me dijeron, bueno, no, creo que eso no lo grabé. Me dijeron, joven, no tendrá, como entré por la salida, no tendrá feria de 200 o 100 que me preste. Traía 120, creo. Y el concepto de prestar, o sea, no me gustó tanto. Entonces le dije, no, nomás traigo 70, doña. Y me dijo, no, pues préstemelo, porfa. Y se los presté. Y dije, pues ahorita me los darán, ¿no? Irán a feriar o no, así. Pues no. Entonces tuve que pedir más comida. Aquí está la gente. Ahorita sigo contando. ¿Qué andan? ¿Qué andan? ¿Qué andan haciendo?
Echándole a comer a los patos.
Güey, cuidado con
Herbert,
buscar que
sí.
literalmente la disquera de Toquilla, man.
¿Qué?
Tienes mierda literalmente ahí.
Qué bueno que no la pisé.
Y creo que alguien la pisó porque no estaba pitada.
Yo no.
Holy la pisé.
Martín, revisa que no hayas pisado mierda.
Sí,
No.
sí, es este.
Valió ver, ya vi.
Igual los veo allá, voy a ver qué hago aquí. Voy a caminar un rato para el blog. Voy a grabar los patos.
Se salgan.
Nos vemos un rato. Mira, pollos. Siempre hubo tantos patos, ¿no? Un montón. No sé por qué ahora se vinieron todos para acá. ¿Qué estaba contando? Lo de la feria, ¿no? Estoy grabando. ¿Hola? Sí. Pues estaba ahí, había pedido una quesadilla nomás, porque aparte también tengo fruta, que seguramente ahorita me la como, pero sí. Traía fruta, entonces dije, pues una quesadilla, mi fruta, y todo piola, ¿no? Pero toma, que le presto los 70. Y no fueron por feria, o sea, creo que la señora sí quiso ir por feria y compró unas palomitas. Pero la de las palomitas tampoco tenía feria, entonces como que se las fió. Pero el punto es que no tenía feria. Entonces me vi en la obligación de pedir otra quesadilla, otra de 30. Cosa que hacía era 60 y los 10 pesos sí me los pudieron dar. Entonces terminé comiendo 2 quesadillas. No sé hasta qué punto me pueda comer la fruta. O sea, creo yo que me lo tengo que comer, no creo que aguante hasta tarde cuando termine todo esto. Entonces seguramente ahorita me siento y no voy a poder comer mi fruta. Pero alguien caminando atrás de mí me está poniendo muy nervioso. Voy a hacerme el güey aquí para que pase. Así estuvo. Supongo que serán de la prepa. Estos. Qué épocas de la prepa. La prepa que fue casi todo en pandemia. Muy divertido. De hecho, ese lugar me trajo varios recuerdos porque el día del examen final, el último que tuvimos, que fue de matemáticas, salimos todos juntos y nos fuimos a comer este puestito de gorditas. Me acuerdo que muchos quedaron devastados con ese examen. Estaba recontra fácil, no sé por qué se les complicaba tanto. O sea, eran muchas cosas para aprender, porque era básicamente integrar. Sí, creo que eran integrales. Era aprenderse los métodos de integración y huevadas. Se le complicó un montón la cosa a la gente. A mí, por fortuna, no. De hecho, yo saliendo del examen yo dije, voy a sacar 10. Pero no me saqué 9. Entonces cagué. le fallé a mi intelecto. Alguna abogada habré tenido mal, no sé, ya ni ganas de preguntarle al profe. El profe era medio y sí, me acuerdo que ese creo que fue la última vez que estuve con mi salón pasado, al menos con todos así reunidos. Ya después me habré juntado con uno que otro, pero uy, me llaman. ¿Aló? ¿Aló? Ah, hola. Seguí caminando para adelante, estoy por los patines. Sí, ¿por qué? Ah, ¿la copa? Vale, sí, acá lo tengo. Sí. Me acaba de llamar Jonan, ocupa la pila. También huevón, yo se lo hubiera dado que estábamos. Pero soy bien distraído, no me ocurren esas cosas. Vamos a hacer un poquito de reversa para toparnos con Jonan. Mira, ahí está. ¿Ven esa cosa? Chamán, está por acá. Ahí. Está Jonan. Está levantando la mano. No sé si se ve en la cámara. Ahí viene. Tomándose su tiempo. Ahí tiene prisa. Hola. ¿Por qué?
Porque mover por allá por 5 señores.
¿Ya se van a su casa?
Sí.
Ah, ¿qué?
¿Quieres terminar lo de Gutiérrez, sabes?
Vale. Justo te iba a preguntar que... Ah, bueno, está en la pila. ¿Que a dónde se iban a meter ahorita?
Bueno, ellos no sé, yo me voy a ir a la casa.
Vale.
Creo que ellos también, porque dijeron que iban a bicentenario.
Venga, muchas gracias. Me está salvando mucho tu pila.
Métete a la conferencia de Aida.
¿Ah?
Métete a la conferencia de Aida.
¿De Aida? ¿Quién es Aida?
¿La que me habló?
La que te habló, Donald. Ah, cuando estábamos en la habitación está toda fría.
Sí.
¿Y
¿No
qué
te
te dijo?
la historia?
No, yo de repente volteé, te vi hablando con una chica y ya, o sea, no supe ni qué pasó.
No le hablé yo, me habló ella.
O sea, te vi hablando con ella así.
Ah, ok. Estás grabando, ¿verdad?
Sí.
Iba a exponer y me dice que si no que era aquí esta sala. Y saqué el que nos dio Leti. Y ya me puse a explicarle. Y de la nada... ¿Qué fue lo que me dijo? Se me fue la onda por los patines. Está chido el patín.
Sí, yo me acuerdo que aprendí aquí.
Ah, me preguntó que si le podía pasar eso. Y dije, ¿me pasas tu número?
Ah,
Y
la
luego ya,
galán, aprovechando.
Sí, me pasó su número. Y supe que se llamaba Aida. Y luego
Aida.
ya empezamos a platicar un rato. Y después le dije, ¿eres estudiante? Y me dice, no, voy a presentar aquí. Y yo dije, ah, caray. Y dije, a lo mejor será como Aldo y Santi, ¿no? Que van a presentar.
Ah.
Y le dije, oye, así por casualidad, ¿cuántos años tienes? Y me dice, 26. Y yo le dije, ah, mira tú, qué chido.
¿Y
Pues,
se veía de menos?
¿eh?
Se veía de
¿Se veía de
menos.
nuestra edad?
Llegando. O sea que tú le quitabas 7 años.
8.
8.
Yo tengo 18, ella tiene 26.
Bueno, pues nuestra generación ya tiene 19, la mayoría.
Claro. Esta es la salida más cercana que hay de la Encantada por allá, ¿verdad?
No, no tengo idea.
A ver, deja buscar un mapa.
Yo me acuerdo que venía de niñito y ahí me metí en ese tronco y me sacaba foto. También me acuerdo una vez que habíamos rentado un patín y yo iba a bajar esa curva. Dije, no manches, voy bien rápido, los voy a dejar atrás. Entonces me bajé del patín.
Ajá.
Pero claro, el momento se conserva, ¿no?
Ajá.
Y me caí y me pegué. Me raspé el brazo y me salía sangre y dije, ¡ah!
En efecto, este es el lugar más cercano para salir, entonces tenemos que agarrar por aquí. Va pues. ¿Vas a seguir grabando?
Sí, estaba contando mis anécdotas de prepa. Es que ahí fue la última comida grupal que tuvimos. ¿Dónde, la verdad, ¿dónde estaba? Ajá.
Bueno, no se nos queja. Adiós.
Nos vemos mañana.
Sí.
Vale, terminaron las interrupciones. Qué huevada. No sé si estaba contando algo cuando me interrumpió. Supongo que sigue con lo de matemáticas. Pues eso. Mientras estaba comiendo ahí me acordé de ese momento después del examen, todos ahí comiendo. Estuvo piola. O sea, igual tampoco es como que la prepa la recuerde como una gran etapa. Pero bueno, pues ahí sí se consiguieron varias cosas buenas en ese época. El último año casi. Todo lo demás de la prepa fue una mierda. Pero bueno. Pues ahorita estoy caminando hasta en el zoológico, me acuerdo que había un baño. Voy a entrar al baño. A ver si no está muy feo, como me dijeron los chicos. Espero que no. Porque si está muy feo, bueno, si está feo o no, ¿qué voy a hacer? No me ponga a limpiar. O que me aguante hasta allá. Aparte me quiero comer mi fruta, pero obviamente tengo que entrar al baño. Me parece que ellos ya se fueron a su casa. Entonces, grabar alguna conferencia más hasta que tenga como una barrita de pila. Ya cuando me quede una barrita de pila, porque ya no se lleva la pila, entonces ya ni cómo cargarla. A lo mejor la compu, pero eso sería muy tardado. Entonces, yo creo que voy, entro a alguna conferencia, cuando me quede una barrita de pila ya me voy. Para ver si se alcanza a grabar el recorrido de aquí a mi casa. O si ya para cuando termine esto ya tengo una barrita, pues ya que lo voy a hacer. Volví. Pues sí, tampoco es la gran cosa. Tampoco es como para adultarse y aguantarse. Igual están pellillos, así que fue una visita rápida. Había un baño todo cagado, así, asqueroso. Por suerte yo iba a orinar nomás. Si hubiera ido a hacer del 2, me hubiera aguantado, obviamente. Bueno, aquí tenemos música. Seguramente con copyright. Estoy viendo el video. ¿Qué va a hacer, no? Me lo van a desmonetizar. Si cobrara. Ahora la misión es encontrar un lugar tranquilo, con sombrita, para comerme mi fruta. Al menos una parte de ella. No haría pena que se echara a perder todo. Y después de eso, pues ir a ver cómo está bien ahí en el Congreso. Pues bueno, no hay nada más que decir. Voy a caminar, buscar un lugar para mi fruta, donde no haya patos. Me da miedo que me toque un pato por mi sandía. No sé qué traigo, no me acuerdo. Pero igual ya estaré solo, porque ya los chicos se fueron a su casa. No sé si mencioné. Seguramente se escuchó que ya no dijo. Entonces, pues bueno. El lugar se ve bien, la brisa está interesante y se escuchan los pollos de fondo. Qué mejor. Yo creo que me voy a poner aquí este árbol. Bueno, no, hay gente. Hay una pareja de niñitos. Entonces, será más para allá. Porque, qué pena, ¿no? Ponerse a comer en frente de la gente que también está comiendo. Yo creo que acá. Bueno, deberíamos bien ponerme acá, ¿no? Tipo aquí. Cosa que tengo una vista así bien chida, ¿no? Echa esa vista, papá. Entonces, bueno, ojalá no llegue alguien más cerca. Voy a comer mi fruta. Y después de eso regreso al Congreso. Vengo a Iguá. Vale, un cambio de plan. Resulta que sí, no tengo mucha hambre. Intenté comer alguna, pero lleno. Las quesadillas estaban grandes. Si hubiera comido una sola quesadilla, hubiera podido comer la fruta, pero ya me estafaron. Entonces ya fue, me comí un poco. Igual no se ve como que se va a echar a perder ahorita, está decente. Entonces seguramente me la coma llegando a la casa. Y ahorita pues ya voy a ir al Congreso. Voy a ver si hay alguna presentación, intro. Grabo un poco porque ya la batería no da para tanto. Lo hubiera cargado bien. Huevón yo, no saber que Jonan ya se iba a ir. Voy, a lo mejor tomo fotos de más. Y ya. Estaré a lo mucho hasta las 4, entonces una hora más. Y ya a las 4 me voy para la casa. Y ya. Jonan tiene razón y tenemos que acabarlo de ecuaciones diferenciales ordinarias, que es un montón, y es para el lunes. Era para mañana, pero por el Congreso nos la amplió un poquito. Y yo no he hecho ni pincho. Entonces sí, igual está fácil, entonces creo que en una tarde la puedo hacer. Voy a ver si esta tarde lo puedo hacer. Aunque seguramente me entretenga editando los videos. Bueno, editando, pegando clips, cortando huevas. Entonces yo creo que le avanzaré nomás, pero ya estos días no lo acabaré. También tengo que hacer una tarea de cálculo 3, porque se entrega el día del examen. El examen es el martes, entonces aparte de la tarea tengo que estudiar. Y el jueves también de la próxima semana tengo examen de programación, que eso en principio tendría que ser fácil. Vamos a ver qué onda. Pero sí, me trae con pendientes las otras materias, pues todo tranquilo. Tuvimos examen de física el viernes. No sé cómo sentirme al respecto, o sea, contesté todo, nada más unas cosas no estoy seguro. En teoría hoy se iba a hacer la resolución del examen, pero si voy me doy cuenta de que tengo todo mal, me voy a deprimir. Entonces prefiero vivir con la duda hasta que me den el resultado del examen, y ya viendo el resultado pues ya veré qué tal me va. Espero que bien, porque pues hay que salir con buena calificación. Pero sí. Entonces ahorita que ya el Congreso, pues seguiré con el video. Ahí. Entonces vamos a caminar, entonces por las huevas. Ahí, venga, bye.
I don't remember everybody's feelings because I'm going to talk about things, very simple physics, extremely simple physics. So I hope I'm very So I suppose you know, but it's good to remember the dielectric properties. Electric dipole moment of a charge, two charges, is defined as E equals to qd, where d is the distance. And remember that the negative charge is a source of field, and the positive charge is a sink. So the dipole goes from the negative to the positive. And of course, if you have three charges, but they are in a line, so P will be 0. So, okay, I mean the electric dipole. But if you lower the green positive charge, you can easily see that there is a component on the y direction that does not cancel, so it gets an effective electron dipole moment. This is just like water. I mean, like yes, like water, right? So there's the dipole moment will be QD in the direction of y. Okay. So let me give a few introductory remarks, and all circuits have three elements, passive elements. A resistor, capacitor, or inductors. You might have amplifiers or things like that are not passive. But passive are only these transistors or a passive element, by the way. So this is the only three. And their resistors and capacitors and inductors are energy storing devices. Okay, so I'm going to move on a little bit quicker. By electron spectroscopy, commonly known as impedance spectroscopy, reveals, measures the impedance. I will go into what is impedance a little more, but it's in force in the case of resistor to with the resistance. His impedance will be that opposes to the change of current. And admittance will be the inverse, it's like resistance and conductance. And you will apply an external electric field at a given frequency, an AC, okay, at omega, frequency omega, okay? Is used in many fields. Okay, so there are many techniques, as you know, to reveal the electrical structure and the electronic properties, materials, and there are few ones over there. So, very well known standard techniques. And of course, there is this is the impedance spectroscopy. Okay, next. So how do you start developing an idea? Suppose you have an idea of doing research. Well, you start by writing something on a piece of paper, and this is what we did. We faced the problem of measuring the electronic properties of a cell in the brain, neuron. If you want to measure the axon, conductivity, there's a lot of controversy. People say that neurons can be very good dielectric, and other people say they're semiconductors. So it's 10 to the 19 difference between those two opinions. What is manual? So surely somebody's doing something wrong. So we thought that maybe if they can, you see, the problem is how do you put a how do you measure the conductivity of a neuron, an axon, that's very small? And even worse, how do you measure the conductivity of DNA? Okay? So we say, well, we're going to make a liquid, we make a suspension of DNA, and we're going to try impedance of the process. Okay? So we measure the impedance, the resistance, so to say. So let's go to the next one. So let's go ahead and go to the next three. So we started playing around at home. I gave a little shot, so I did this. And the idea is to have a small cage with two electrodes, fill it with a liquid, and then measure this electronic properties. Okay? So next, please. So this is right PDA or somewhere else. So somebody also thought of this. So finally we ended up with this. Okay? Those are the two vials. This is the cage. You need to isolate from electrical noise very well. So this is a cage made of aluminum, and the cage, the cell with the liquid suspension will be here. These are the dials with the DNA in suspension in water, of course very few water, and micropore water. So let's go to the next one. And okay, you can see it a little better. There's the cell. It's let's see if I can see it better. Okay, next one. This is the cell. There are two electrodes that go outside. This is the yellow and green. They are connected to the outside to two coaxial edges. You can see one here. So let's go to the next page. Okay, there is. This is a quartz tube, you can say. Now that it broke down, but we have to have it open at the two sides and put the electrode on the side. Next, please. Okay, this is the way to prepare DNA. Very sure familiar with this all the night. But what you do is this comes from the Escherichia coli. You have to blow this little place, and then you have to change it for a long time. Then you do centrifugation, and this is where you get DNA, and so in a liquid. Okay? You have to evaluate the concentration and purity of nanodrop, and agarose help electrophoresis like this technique. I don't know if you're familiar with that. But anyway, this is precision. Precision. We use a precision LCR meter. Okay. And you can have frequencies, very low frequencies. This is millihertz. It's almost stationary, right? There is no changing, but it can be very quickly to 1 megahertz. And I couldn't get rid of this, so let's see if we can try to get rid of that. Right? Sorry. I can do better than that. Next. I guess we get it there. Next. Now we're very good. Okay. But I think you can do a bit better. Next. That's not grand order. Anyway, so you have this meter, and it's connected to a Over here, you see the case, and you do the measurements. Okay? So next, please. No. Okay, so we are taking measurements. Once you manage to understand what the measuring technique is, it's very simple. You have to push button. And it is computer controlled, and they get the program ready. So, next please. This is what you get. You get a bunch of numbers, right? And of course, this is a very important thing, how to analyze this. So there's people, there's a lot of jobs to be done here. So you need frequency and phase in degrees, and you can also measure the gradients. So let's go to the next one. You apply 1 volt and you sweep the frequency. Okay? Next, please. So it can be very cumbersome. You see, the equations are can be very impressive. You have to do really a good job in extracting the information. And when you finish extracting that, you can make a model which can be a capacitor, resistor, and non-capacitor, for example. Combinations of capacitor, inductors, and resistors. This is going to be your model. This is what you're looking at. So next, please. Okay, this is interesting because, as you know, if you are in a very low frequencies, charge accumulation on the sides, and the impedance will be then the impedance of this part, where the charge is accumulated. On the other side, it will be a negative charge accumulation, and in the middle it will be bulk. So you have to be able to get rid of these two impedances on the sides. Let's go to the next one. Same thing. Next, please. Okay, so there are many ways you can do it. Okay? If you have simple circuit like this, an RC circuit, your measurement will be the imaginary part of the impedance. Impedance will be a complex number. The real part is the resistance, and the imaginary part have an inductor, capacitor component, right? And that's imaginary. So, if you plot the imaginary part of Z, actually the minus, versus the real part, you will get a circle, perfect circle. Okay? And for other example, if you have a little bit complicated circuit, you will get 2 circles. Okay? Now, if you plot now the imaginary part of the difference, it's only the inverse of this. You wear a peak at a given real difference. And in the same with this circuit, look, you have another, again, you get a circle and a line that goes to infinity. Okay? Next, please. Okay, so our first measurement looks like that. You make the measurements, and it looks like that. And you can see it on a screen, and then this is what we got. Look, we didn't get much. We have 2 measurements there. One is without DNA, and this is with DNA. The black one is with DNA. Look, we are plotting against the real part of Z, and on this imaginary part of Z. So you see, you always get, this is after analyzing, okay? But you get This is the measurement you get, and after you make the model, then you get almost a circle, and only this part for the sample DNA. Next, please. Okay. Okay, so I can go a little bit slower. Okay, so the next, we make the next, we measure another concentration, and we got a bit better result this time. You see, this is with DNA, we're plotting it then, minus the imaginary part of impedance versus frequency. Okay? And you see we go to low frequency. In this case, not that low, this is about 20 or so, 20 hertz, up to 1 millimeter. And of course, you don't see much here, but the idea is to make a sort of a quick run and then look for the timing details, golden details, okay? And this is when you do this graph things. The final idea is to see if we can make a measurement that can give you an idea of where the DNA has some genes that are that can promote cancer. Okay? And if we're lucky, so it will be a very, very quick measurement. You make a quick measurement for about half an hour, and then you will have to look for little detail. It takes a lot of computing, but then we look at little detail, and it's not going to be an easy task, because as you know, DNA can have a diameter of 10 nanometers, and it can be as long as 2 meters long. So if a few of those have a gene that is will express itself in cancer, then we would like to see if we can detect it before it expresses. Okay? So it's a very important, very useful thing. On the side, it would be it's really cheap, really. And we only get water, microphone water, very, very, very few water. And this is almost all an DNA that can be extracted by a professional person. So we hope we have just started this project. We don't have any results or any conclusive results yet. We have not even yet. I took this measurement on Friday before coming. So we hope we don't have to go into a more complicated cell, like this is a 4 electrode cell. Ours is a 2 electrode cell, and maybe we might have to go to a 4 electrode cell. We don't know. Okay, and then you start complicating the things. And next, please. So we don't know if it is going to be necessary. And if you like to know the answer to this question, go to Estaba next year. We're going to have the conference next year. Okay? So next week. Okay, so maybe I didn't. Okay, I have some other collaborators that didn't mention, and they're very special. You know, they're all my colleagues, all my students, and there are some that never there is family and never contradict me, and they are the family. Thank you, Father. Thank you very much for your attention. Oh, by the way, we also have a Zacatecas collaborator. There's a